find delta such that this is fulfilled. This condition is fulfilled, and epsilon was given to us. We have two different epsilon values, but we're going to just look at one of the two. The procedure is identical for the other one, of course. So remember, every time we look at the absolute value less than a number, let's say 2, we have to rewrite this inequality. We don't know how to solve this, but we know how to solve this that replaces the absolute value inequality. You don't have to cross it out like that. I was just making a point. So when I'm looking at this and when I know I have to solve this inequality for x, why am I solving for x? Because I want this. I want to start here and I want to get this. If I get the absolute value of x on the left-hand side, whatever number I get on this side is delta. So I change this into negative 0.5, exactly how I did this. Less than e to 2x minus 1 over x minus 2 less than 0.5. I find in the middle the least common denominator, e to 2x minus 1 minus 2x over x less than negative 0.5, greater than negative 0.5, less than 0.5. And now I have to solve two equations. In order to be able to solve this, I have to solve two equations. This equals this, and this equals this. So e to 2x minus 1 minus 2x over x minus 0.5 equals 0, which is this equation moving 0.5 to the left. And e to 2x minus 1 minus 2x over x moving this to the other side plus 0.5 equals 0. At this point, we don't know how to solve these equations by hand. We will have a very important method, as I said in chapter 4. So this is e to 2x. I find the least common denominator, minus 1. Minus 2x, but minus 0.5x will be minus 2.5x divided by x equals 0. That's the first equation. And the second equation will be minus 1.5. Find the least common denominator. E to 2x minus 1. Minus 2, but plus 0.5x will be negative 1.5x divided by x equals 0. So now I'm going to solve these two equations. And I have to use the graphing calculator. Any questions so far? Andrew, you can shut the door if the noise bothers you. Or ready? Okay, in y equals. So clear if you have anything, and let's put parentheses around the top. E to 2x. I like parentheses. I don't trust this system. So minus 1 minus 2x I'm sorry, 2.5x. Close the parenthesis for the top and divide by x. Since there is only one term in the denominator, it's okay. So now I go to secant and calc, and I want to find the 0 or the x-intercept, so 2. I wait till the graph finishes up, so I see there is an x-intercept between 0 and 1. So we go to secant and, I'm sorry, I want the left bound, 0. I didn't mean that. Sorry, I messed up. Sorry. Okay, so it's asking me for the left bound. I'm going to put 0. It's asking me now for the right bound. I'm going to put 1. I'm not going to guess. I refuse to guess. And I press enter again, and I get 0.215. So x equals 0.215 from the first one. And now I repeat the whole process. I go back to y equals and replace negative 2.5 by negative 1.5. So all I have to do is overwrite 2, change 2 into 1. And I go back to secant and calc. I want a 0. It crosses now on this side between negative 1 and 0. So I want negative 1, enter 0, enter no guess, just give me the answer. Negative 0.3029 or negative 0.303, because I think I think they want 3 decimal digits. So after doing that, the question is kind of tricky. It says, what is the maximum? And you know, bless you, you know there is no maximum here. We have to choose the smallest of the two. So this one implies the absolute value less than 0.215, which is delta. This one implies the absolute value of x less than 0.303, which is delta. You cannot choose the largest of the two. But you can say the largest possible that I can choose is 0.215. That's what they meant. Any questions on this problem? Any questions? No, is this better? Mm-hmm. Okay. Other questions for me? Anything else? Did you try anything else? Do you have questions on anything else? Okay, we're back to page 141. And I would like us to choose a problem in which we show our understanding of these functions. So I'd like to choose any problem you like from here in which we are given conditions and we're asked to come up with an example of a function. Which one? Which one? Any preference? No preference?
7.
Which one?
7.
7. Very good. So let's look at 7. So we're looking at 7 on page. Did I change that limit? No. Okay, so this is problem 7 actually on page 140. And this is limit. I have to copy all these conditions. Limit as x approaches 2. Is it from the left? No, from either side. Of f of x equals negative infinity. Limit as x approaches infinity from f of x is infinity. Limit of f of x as x approaches negative infinity is 0. Limit as x approaches 0 from the right of f of x is infinity. And finally, limit as x approaches 0 from the left of f of x is negative infinity. Of course, there is more than one correct answer here. We're just going to come up with one example, and I'm sure you can come up with another. Okay. Remember what we do in these situations. I strongly recommend summarize all this information in a table. It will be so much easier to put it all together. So let's do that. So first of all, I see 2. So if this is 0, I'm going to say this is 2. The limit from either side of 2 is negative infinity. Negative infinity inside of this parenthesis. Negative infinity inside of this parenthesis. And this is done. Limit as x approaches infinity from f of x is infinity. Okay, fine. Done. As x approaches infinity, the function values go to infinity. Limit of f of x as x approaches negative infinity, that is 0. That is done. Obviously, y equals 0. Horizontal asymptote at negative infinity only. Now I see some information about 0. Okay, let's say 0 is here. The limit from the right of 0 is infinity. Done. The limit from the left of 0 is negative infinity. Done. Did I do something?
Oh, the projector just went out for a second.
Oh no, please don't do that to me. Please don't do that to me. Thank you. Sorry, sorry. I didn't even pay attention to that. I was focusing here. Okay, it's kind of dark outside. Do you think it's gonna start something? I don't care. I like the rain, but I just don't want the power to go out. That's all. I consider x equals 0 a vertical asymptote, and I consider x equals 2 a vertical asymptote. The limits left and right are infinities. So therefore, here's my example. Any questions on how we organize the information? Any questions? Okay. So I will draw x equals 0, which is already, it's an overkill. I will draw x equals 2. And of course, this is another overkill. Y equals 0. The horizontal asymptote. So now, from approaching 0 to approaching negative infinity, these examples are extremely useful. You'll see when we get to graphing. And then from positive infinity to negative infinity, you can do whatever you want. I'm going to do this. And then from negative infinity to infinity, fine. And this is my graph. It complies with all the given conditions. From approaching 0 to approaching negative infinity. From approaching positive infinity down to negative infinity on the left-hand side of x equals 2. And then from negative infinity to infinity on the right-hand side of x equals 2. Any questions on this example? Are we okay with this? Yes, everyone? Okay, perfect. Now I would like to choose one example in which we're asked to determine all information, let's say 43. You'll see in a second, 43 on page 141. We're given y equals 2x squared plus x minus 1 divided by x squared plus x minus 2. So here's the question. Find the horizontal and vertical asymptote of each curve. If you have a graphing device, which I don't need to, check and work by blah, blah, blah. In addition, I need to find all the limits that pertain to the vertical and the horizontal asymptotes, of course. Okay, what type of function is this? That's my first question to myself, if you want. I need to identify the function. What is it? Say it again. The top is quadratic. The top is a polynomial, the bottom is a polynomial. There is no polynomial that has a fraction in it with x in the denominator. Very good. It's a rational function. Rational functions can encounter the following three situations. One of them is vertical asymptotes. When will a rational function have vertical asymptotes? When x squared plus x minus 2 equals 0. When it's undefined. Hole in the graph. A hole in the graph is a special situation, specific case in which, let's say I have something like this. Obviously, the function is undefined at -1 and 3. There is no discussion there, correct? But because I can simplify this factor, in other words, x equals -1, is not a vertical asymptote, but a hole in the graph, because the factor went away. The simplified form is x minus 1 over x minus 3. The factor in the denominator that stays remains as a vertical asymptote. But x equals -1 is not a vertical asymptote, because that factor in the denominator was removed with an identical factor from the top. Another situation, horizontal asymptotes. Now, this is specific to two types, not to all types of rational functions. Specific to the ones that have the same degree over same degree, or the ones with a higher degree in the denominator. Okay? So horizontal asymptotes in two situations. One situation is degree n, degree greater than n, higher degree in the denominator, and degree n over degree n. If they are the same or higher in the denominator, that rational function will have a horizontal asymptote. If it's anything by 1 degree higher, so if it's degree n plus 1, and this is degree n, this is the only situation with a slant asymptote. The only situation. If it's degree 5 at the top and degree 2 at the bottom, no horizontal, no slant. So we're going to get to this in chapter 4. So you don't have to memorize this. I'm just going to review this with you. I'm going to look at it again. So rational functions can have vertical asymptotes, can have holes in the graph, can have horizontal asymptotes, or vertical, or slant. Okay? Vertical, holes, horizontal, or slant. But it's specific to one situation when there is a slant asymptote. Only when this degree is like 3 and this one 2, 4 and 3, 10 and 9. So the top is 1 degree higher than the bottom. We're going to get to slant asymptotes again in chapter 4. So I'm coming back to this. I'm going to try to factor completely the top and the bottom, identify vertical asymptotes and find the limits left and right, and also determine the horizontal asymptote. It's the same degree of a same degree. It's not this situation. It's this situation. Same degree of a same degree, so obviously there is a horizontal asymptote. Ready? So I'm going to copy the function. So f of x equals, the denominator factors into x plus 2, x minus 1. And what can you say about the numerator? How do we factor the numerator? 2x squared plus x minus 1. Two x squared plus 2x minus x and minus 1. The reason why you can say, well, when you determine horizontal and vertical asymptotes, why do we factor the numerator? Because I need to check to see if there is a hole in the graph. There is none. X plus 2 does not do away with the factor from the top, and x minus 1 doesn't go away with the factor from the top. So therefore, there are no holes in the graph. So obviously, x equals negative 2 is a VA, and x equals 1 is a VA. They don't go anywhere. They stay in the final form. But this is not sufficient. I have to determine the limit as x approaches negative 2 from the left of 2x minus 1, x plus 1, x plus 2, x minus 1. And then the other one, limit as x approaches negative 2 from the right, 2x minus 1, x plus 1, x plus 2, x minus 1. We'll find them in a minute. I'm going to write the other two, and then we'll come back. So limit as x approaches 1 from the left, from 2x minus 1, x plus 1, x plus 2, x minus 1. And finally, limit as x approaches 1 from the right, 2x minus 1, x plus 1, x plus 2, x minus 1. Yes, you can put the function in the graphing calculator and just punch in negative 2.1 and negative 1.9. from left and right, the same thing with 1. But really, it's not that difficult. So coming back to the first one, negative 2 from the left is like negative 2.1. I know that this is negative. 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 4 negatives, the answer. It will take me longer to punch in the function in the graphing calculator. And if I don't put enough parentheses, I may even make an error. So left of negative 2 is negative 2.1. Minus, 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 minus. So 4 negatives. How much? How much? 4 negatives. Good. Okay, so with negative 1.9, negative, but positive. Oh, no, negative 1.9, still negative. 1.9, negative 1.9, this is positive, and this is negative, 3 negatives. Good. So now with 1 from the left, I'm using 0.9. So this is negative 1. Because this is positive 1.8 minus 1, so this is positive. This is positive. This is positive, but this is negative. So what is the sign? Yes. And then 1.1, positive, 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 positive. So we determine the vertical asymptotes. There are no holes in the graph, and we determine the limits left and right of each. So if we were to graph this function now, we had both limits left and right of each vertical asymptote. Now we have to find the horizontal asymptote. So limit as x approaches infinity from 2x squared plus x minus 1 divided by, it was, yes, x squared plus x plus 2, minus 2. Good. So how do we determine, and of course it's not going to change if we determine a negative infinity. So how did we do it last time? We know that it's infinity over infinity. This is an indeterminate case. Anything can happen. So then limit x approaches infinity. What did we do?
X squared.
Yes, because the degree at the top is x squared, and the degree in the denominator is also x squared. We need 3 terms in parentheses. And they are
X to the 1.
2 plus 1 over x. Yes? Awesome. And then?
1.
Perfect.
1 over x.
Perfect.
Minus 2 over x squared.
Good. Now, this is our next step. We know that only when x approaches infinity, not 1/2 or 1/3 or anything like that, right? These all go where?
0.
Yes, they all go to 0. Perfect. So then the horizontal asymptote will be 2. So y equals 2, horizontal asymptote. A rational function cannot have a horizontal asymptote and also a slant. That's not possible. The slant is only in one case, when the degree at the top is exactly by 1 unit higher. So you don't have to look for anything else. And yes, it's a horizontal asymptote on both sides. We did not use the fact that it was positive or negative. Any questions? Any questions? Okay, the last 2 sections, I always present the last 2 sections together of this chapter, but I always start with 2.8. You'll see in a minute why. So 2.7 and 2.8, and I'm not going to put the title of 2.8 just yet. I'm going to come back and put it in. I don't have any secrets, but I just want us to build the knowledge, and then we'll come back and put it in. And yes, I know. We've seen this like 10 times already. I know it's already boring. If this is P and this is Q, you already told me that if this is X, how much is this? Perfect, thank you. And of course, this will be x plus a little bit because they are very close to each other. What will this be?
F of x plus
Of course, thank you very much. And of course, you remember we determined the slope of this line, the slope of the secant line PQ. Can anyone give us the slope?
f of x plus h minus f of x over h.
Good. And we know that this is, and we calculated for several functions,
The difference.
the difference quotient. So we had, so far in this chapter, we learned two concepts. One concept was the difference quotient, which is the rate of change of a function between 2 points that are close to each other, the rate of change. And the other concept that we worked on was, it starts with L.
Limits.
Of course, we're going to put these two together now. The limit concept and the difference quotient concept. So instead of saying what happens to the slope of the secant line PQ when h approaches 0, it will be approach the slope of the tangent line at P, of course. We're going to put the limit in front of the difference quotient as h approaches 0. Is the same concept. We had to study them separate, and now we are able to put them together. So what do you think this will equal to before you give me the final form? So once, instead of writing this, now I put the limit in front of the difference quotient. That must be the slope of the tangent line, right? As h approaches 0, meaning q gets closer and closer to p, the limit as h approaches 0 of this is nothing else but the slope at p, of the tangent line at p, correct?
Yes.
So this is definitely the slope of the tangent line at P. At any point, there is a condition here. So at any point under, I'm not going to give the condition just this moment, under certain conditions. And I'll explain the conditions in about 5 minutes. This whole thing has a name. And the name is,
Derivative.
thank you, f prime of x. So it's the derivative of f of x. The derivative function. The derivative function of f of x. Of function f. Okay, so what does f prime mean? Number one that we've seen so far is the slope of the tangent line to the graph of f of x is the slope of the tangent line to the graph of f of x at any point x, and now the condition, where the function is, anyone remembers? It's okay if you don't. You don't have to. Say it again.
Define.
Nope.
Continuous.
Nope. Much stronger than that. Differentiable. I have not talked about differentiability. I have not explained what that means. So in a minute I will. So first I just want to list what f prime means. So f prime is the slope of the tangent line to the graph of f of x at any point x where the function is differentiable. Now, f prime of x is a function that gives the slope of the tangent line to the graph of f of x at any point. Number two, is the instantaneous velocity. Of course, if f of x is a distance. And number 3 gives the rate of change of a function at any point where the function is differentiable. The rate of change of f of x at any point where f of x is differentiable. So when we put together the difference quotient with a limit, we get the instantaneous velocity, we get the slope of the tangent line, and the rate of change of the function at that point. They all mean the same thing. They're all calculated the same way. So let me read this back to you one more time just to make sure that you're on the same page. So the first derivative, f prime or the first derivative, is the slope of the tangent line to the graph of f of x at any point, or gives the slope of the tangent line to the graph of f of x at any point where x, where the function is differentiable. F prime is a function, it's not a number, unless we plug in to find that specific number. The instantaneous velocity, so f prime is also the instantaneous velocity anytime when f of x is the distance function. And also f prime gives the rate of change of f of x at any point where f of x is differentiable. Same thing, the instantaneous velocity and the slope and the rate of change, they're all the same. Okay. Before we are going to look at different functions and find their derivative, I would like to talk about differentiability. Okay. When is a function not differentiable? Here's how we recognize it. One option, when is a function not differentiable? One option is when it's not continuous. If a function is not continuous at a point, it cannot have a derivative at a point. If it's either not undefined or a jump, or if it's not continuous, it cannot be differentiable there. Second option, a function is not differentiable if it has a cusp or corner. If it has a cusp or a corner, the function, I'll explain, it's not differentiable there. When a function has an infinite tangent, I'll give you examples from all three. If a function is continuous but has an infinite tangent, at that point where the tangent is infinite, the function is not differentiable, does not have a derivative. So now, two other things that I would like you to remember, and we'll have an example for sure today, is this. F prime discontinuous at x equals a implies f of x not differentiable there. We're going to graph a derivative. We're going to be given a function, we're going to graph a derivative, and we will see that when a derivative is not continuous at a point, it will automatically tell us that the function is not differentiable there. Or vice versa. If the function is not differentiable there, you will see the derivative is discontinuous there. It has a jump. So that's something else to keep in mind. Okay. So let me give you those examples. So this is an example of not continuous. So how come that the function is not differentiable here? It's because it has two tangents. So this function is differentiable at p because there is a unique tangent at p, just one. The tangent from this side has the same slope with the tangent from this side. Same slope, unique tangent. Same thing here. There is a unique tangent at q, which means the function is differentiable at q. But here at 1, the function does not have a unique tangent. Look at the tangent here. Let's say the slope is 1. And look at the tangent here. The slope is 2. I don't even have to identify them. It's not important. It's not unique. The tangent is not unique. See? 2 tangents. Okay, let's look at the cusp or corner. They're 2 different things. So here's a cusp. Like how 2 teeth look like, one next to the other. As you see, at this point, there are 2 tangents. A tangent with a negative slope and a tangent with a positive slope. Although the function is continuous, it has a cusp, and the function is not differentiable at that point. It has 2 tangents at that point, not a unique tangent. It does not have one tangent. Okay, and let's look at corner. We know the absolute value looks like this. The absolute value is not differentiable at this point. It's differentiable everywhere, but not at this point, because there are 2 tangents. One with a positive, one with a negative slope, and one with a positive slope. With your permission, I'm going to get a coffee. Okay, so the infinite tangent. I'm fighting a little bit of something. I'm not sure what it is. Okay, so here's a function with a vertical tangent. So this is cusp. This is not continuous. This is corner. And this is infinite tangent. In all those situations, the function, although it's continuous, is not differentiable. So one more note. Unique tangent. If a function has a unique tangent, at that point, then f is differentiable. So keep that in mind. Yes, please, Eddie?
Can you explain the tangent better, or why?
Right. So here's an example. Let's say f of x equals the cube root of x. And since my next step is I have to determine the derivative, let's find the derivative of this function. Using the definition of the derivative. So coming back, I don't have to go back. I have to write it one more time. So f prime of x equals the limit as h approaches 0 from f of x plus h minus f of x divided by h. This is the only definition of the derivative. Definition of the derivative function. There is only one. So the question now is to illustrate what happens with that vertical tangent. We can illustrate with the cube root of x, or we can illustrate with the square root of x, which is easier. We have to. Let's look at f of x equals the square root of x. because it's easier. So we want to find f prime of x for this function. We don't know what the square root, what is the derivative of the square root of x. We don't have it. We want to determine it. We have to use this definition. We don't have anything else right now. In the next chapter we will. We will know differentiation rules. But right now we don't have it. So I have to write the limit as h approaches 0 from what?
Square root of x minus h. Or x plus h, sorry. Minus square root of x over h.
Excellent. We plug it in, and of course, what are we going to get? Right? What do we do? Very good. And the answer is, I will write the denominator, and you tell me the numerator. Of course, it has to be plus. Sorry. The conjugate. I said the conjugate, but I didn't write it. So we're calculating the difference quotient, right? What has to happen? All terms without h from the top have to go away. And eventually, has to disappear. Okay, good. So please give me the numerator. I didn't forget your answer, your question, Eddie. The answer at the top is? Good. I don't like to do this, but assuming we are simplifying these two, what is left? Where does the numerator go? 1 and the denominator?
So 1 over 2 square root of x.
Good. Coming back, can anyone give us a domain of this function? Awesome, thank you. Can anyone now, so this is the first derivative of the square root of x. Can anyone determine for us the derivative, the domain of the derivative? It's not the same.
Parentheses 0 to
Right. Right. So we conclude that f of x is or is not differentiable at 0. So look at the graph now. I'm trying to answer the vertical tangent. Here it is. So at x equals 0, the function has a vertical tangent. It's the derivative is undefined. Therefore, the function is not differentiable at 0. We could have illustrated with the cube root of x, but the cube root of x is a little bit more difficult to see, to calculate with the limit of the difference quotient. That's the cube root of x. Same thing here. It's a vertical tangent. The derivative will not exist. It would be undefined. Is that better?
Yeah, that's it.
Very good question. Okay. So I would like us to pick a problem, another function other than the one that we just looked at. And from now on, moving forward, we have to forever remember this. What did we say the square root of x prime was equal to?
1 over 2 square root of x.
We have to remember this forever. This is our first result. Okay. Before we graph the derivative, so I'm going to ask you to choose a graph from here so we can graph the derivative. But first, let's choose a function and find its derivative exactly as we did a minute ago with the square root of x, to illustrate with the definition of the derivative. Just any function you want. Please choose. Which one? 2,5 you said? This one? Okay. F of x equals x squared minus 2x to the third. Okay. So this is problem 25 on page 163. I need to caution you that because of x cubed, it will require some work. And because we would like to cut back a little bit on the work, not because we are lazy. I just want to refresh your memory on this. This comes from either combinatorics or Pascal's triangle. And the formula is a cubed plus 3a squared b plus 3ab squared plus b cubed, so we can cut back on multiplication. Do you have to memorize it? No, but then you have to do it by brute force, right? Multiply 3 times. Okay, so keep that in mind. So we are given this function. We want to find f prime of x. We only have one definition, which is limit. Can anyone help? Good, right? From f of x plus h squared minus 2, x plus h cubed minus x squared plus 2x cubed divided by h. See the difficulty with this function? This is no problem, but I have to use this formula for x plus h cubed. Otherwise, it will take me longer. So, can anyone dictate the next step? Be prepared that I will run out of room. I always do. So please give me this.
X squared plus 2x plus x squared.
Thank you very much. Minus 2. Let's write this out first. X cubed plus 3x squared h plus 3x h squared plus h cubed. This is this piece. Eventually I'll distribute 2. Minus x squared and plus 2x cubed. Before we continue, two things must happen. If they don't happen, I have to go back to the drawing board. Start from scratch. I made an error somewhere. What are the two things that have to happen? Without h must go away, and eventually this will cancel out with something from the top. Yes. So always this is your checkpoint. You should always think in those terms. If those terms don't disappear, I have an error. Okay, for now I'm just going to get rid of these two, so I don't have to write them again. And then limit as h approaches 0, 2xh plus h squared minus 2x cubed minus 6x squared h minus 6xh squared minus 2h cubed and plus 2x cubed, everything over h. Whoever chose this problem will not choose for the next, no, I'm kidding. Okay, so 2x cubed with a negative 2x cubed. Every term without h is gone. Obviously, I will factor out what from the top? The problem, right? Because yeah, I know it's 0 over 0. It's 0 over 0 because of that h. Once I get rid of h, it's not going to be 0 over 0 anymore. So limit h approaches 0. All terms have h in common. That eventually will eliminate the denominator. So what do we have? A 2x a positive h, and minus 6x squared, and minus 6xh. Of course, I ran out of room. Minus 2h squared. Is anyone surprised? No. Okay, perfect. So these two go away, of course. And now, only now, I can drop the limit operator. And then what do I get? This approaches 0, this approaches 0, this approaches 0. And the answer is?
2x minus 6x squared.
This is the derivative of the given function, x squared minus 2x cubed. Any questions? Any questions? Okay. I would like us to select any graph from here. Any graph. We are going to graph it. I'm going to copy it to the best of my abilities. And we are going to graph underneath it the derivative function.
10.
10 it is. Was that Chris? Or we should ban him next time. Just kidding. So we pick number 10 on page 162. Allow me to give it the best shot. Make sure that you write, that you draw identical one under the other, because I'm going to use the same x values, the same x on both sides. So please, the y-axis have to be exactly one under the other. So I'm graphing f of x. So it appears to be something like this. That's the best I can do. Okay. A function f prime of x will have as close of a shape as we can get to. Will be far from being exact. Okay. I will pick some points on the function. I'm going to pick this point. 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 And let's say another point here. Graphing or plotting 1, 2, 3, 4, 5 points, it's not going to be an exact graph, no matter what. At each and every point, I'm going to draw a little triangle with a tangent, and I'm going to estimate the tangent. So obviously it's a negative tangent. I'm going to say that this appears to be like 4 and 1. And you can say this is voodoo. No, I have to estimate somehow, right? So this is a tangent at this point, my first point. I have to form a right triangle. I have to determine the rise and the run. And I think that this is 1, 2, 3, 4. So it appears that this is about 4 and this is about 1. So this will be negative 4. And at this point, I have 1, 2, 3, 4. This will be my first point. For this x value, the slope of the tangent line at that point, I determine it to be negative 4. You can say it's negative 3. I will have to agree. I don't know. But I'm not far from the truth. Okay, now at this point, I will draw a tangent. I will try to form a right triangle. I don't know. I think that this is maybe 1, and this is maybe 2. Obviously, this tangent still negative, but it's not as acute as this one is. This is definitely much stronger, much faster than this one. So 1/2, rise over 1, but still negative. So I'm going to say it's here. At this point, I'm going to draw another tangent, and I'm going to form a triangle. And I think that this is more acute than this. It appears to be. I'm going to say 1, 1. So I'm going to say this is -1. There is no question that here the slope must be 0. All this time, the function goes from big slope to small slope to bigger slope, but then still negative but approaching 0. So from big to small to big to negative, and then coming up to 0. So that's my assessment for that part. Moving on. From this point, it's definitely positive all the time, increasing. So I'm going to say maybe the 4/1. 1, 2, 3, 4. So then the graph continues like that. Is this a perfect graph? No. Can't be perfect. But from this point till this point, the function is always negative. The derivative is always negative. The function is always decreasing. Its derivative has to be below the x-axis. From this point on, it's increasing. It's 0 at this point. The slope is 0, horizontal, tangent, and goes on to infinity. It's a good exercise in order to understand what's happening here, especially for the next sections. Any questions here? Now I would like to go back. So obviously 2.8. Now we can write the title. 2.8 is the derivative function. Yes, please. Any question?
There was a graph on one of the examples.
Yes?
I didn't know it could have a derivative because it wasn't differentiable.
If it has a corner, if it has a cusp, or a vertical tangent. So none of these points on this graph are corners, cusps, or vertical tangents.
No, one of the examples from the book.
Oh, okay.
I thought it did number,
You said 10. I copied 10.
Number 11.
Yes. Yes. So right here, the derivative will go to infinity. Will be infinity, positive infinity.
Okay. Is what I mean.
Yeah.
That wouldn't have the derivative.
Yeah, that's true.
Okay.
The derivative function will not be continuous at this point. If the derivative is not continuous, the function is not differentiable. So obviously 2.8 was the derivative function. And now we go back to 2.7 because it's a application of 2.8. 2.7, that's why I always present 2.8 and then I go back to 2.7. Okay, so I promise this is kind of the last time for a while in which I show you the same graph over and over. Okay, this time I don't have a general x, I have a. What is the height here? Perfect. And now this is the generic point, x. And what is this? Please give me the slope of the secant line. F of x minus f of a over x minus a. And now when I put the limit in front, careful, tell me what to write. There is no h here. Careful, tell me what you want, what you need to write when q gets closer and closer to p. Very good. Thank you. As x approaches a. But this is, since x approaches a number, this will be a number. This is not a function. So then what will it be equal to or denoted by? F prime of a. You can say, I don't care about your definition about f prime of a. Give me any function, I'll find f prime of x and plug in a. Well, I don't care about that. Sometimes that is an easier definition to apply than just finding f prime of x and then plugging in a. So this is not the definition of the derivative. It's a definition of the derivative value. So the function, the derivative evaluated at the point. So f prime of a is a number, not a function, and it represents the value of f prime. The value of f prime of x at x equals a. But determined directly, not through the definition of the derivative.